sequential processes term here.
Okay, thank you. So this talk will be about easy classes, easy subclasses of self-avoiding walks. So we've heard a lot already of self-avoiding walks. Here's one on the square lattice, and in this talk I will stick to the square lattice all the time. So you've probably understood that determining C of n, that is the number of n steps self-avoiding walks, is a rather difficult task, and at the moment we mostly have some predictions that deal with the asymptotics of these numbers. So they are supposed or strongly believed to behave like some mu to the n, and mu is about, that's just an estimate, 2.64, and this is corrected, so that's mu to the n, that's the main, well, exponential term, corrected by some rational power of n, and a constant which I have written between brackets because I tend to forget denoting constants. So there are some other very interesting predictions. One of them deals with the end-to-end distance in a random self-avoiding walk of length n, and this is supposed to behave like n to the 3/4, whereas, as you know, it would be square root n for a simple random walk. And you have here pictures. One of them, I think Tom recognizes it. I stole it from his web page, and this one I could do myself. Okay, so this tells you how difficult this problem is. We just have conjectures on the asymptotic number of walks, so this is probably far beyond the reach of people like me who work on exact enumeration. And so this difficulty has motivated for people working on exactly solvable problems the need to design some subclasses of self-avoiding walks that have to be, on the one hand, natural, that they must have a nice definition. They should be as large as possible. I mean, you don't want to count walks formed of north and east steps, for instance. And of course, they should be still tractable. So that's maybe a peculiar game. You have to foresee, in a way, what makes a model exactly solvable. But that's the rule of our game. So there are two objectives. One of them, which I think is probably a bit too ambitious, is to get a better understanding of real self-avoiding walks. At the moment, we are very far from that. For instance, I think that most interesting walks that we can solve exactly, they have a linear end-to-end distance. So that's rather boring walks. And in passing, we hope that this will be the occasion of developing new techniques in exact enumeration. So in this talk, so the title of the talk sounds like a survey, but there is no survey in 25 minutes, I guess. So I'm going to describe two models. The first one is some kind of toy model that everyone thinks about after half a minute. It's been solved lots of times. There's nothing mysterious about it, but it will be the I will take it as a pretext to introduce some important tools in exact enumerations, like generating functions mostly and what you can do with them. And then I'll come to another model that was solved recently that is actually not so hard to solve. We'll solve it together. But happens to be, in a way, the largest class that is solved exactly at the moment. Okay, so let me start with my toy model. I say that the self-avoiding walk is partially directed if it contains at most 3 types of steps. So it avoids one of the 4 steps. So for instance, this is a north-east-west walk, not a new walk, because it doesn't contain any south steps. Okay? And why are these objects easy to count? Well, there's a simple argument for that. You want them to be self-avoiding, but given that you have no south step, the only thing you have to take care of is that you don't do a west step followed by an east one, and conversely. So this means that the self-avoidance condition has become something local. Instead of remembering where you were in the past, you just need to remember what was your last step. Okay, so that's easy, and it will make our task very easy if we want to compute A of n, so the number of n-step walks. So I'll first do it in a rather naive way, what you would do. So there's an initial condition. Here's the only path with 0 steps. And then these pictures tell you that there are 5 types of self-avoiding walks of positive length. So the ones that only consist of horizontal steps, there are 2 of them in each length. And then for those that contain at least 1 north step, you look at the last north step, and it is either followed by nothing, you have A of n minus 1 walks of this type, or it's followed by a horizontal path, and you get this term here in the recursion. So K here would be the length of the purple path here. Okay. So that's an easy recursion which you can solve, and for instance, by introducing these famous generating functions. So this A of t, it's a power series in some indeterminate t, and the nth coefficient of which is the number we are interested in. And then this recurrence relation translates into just a linear equation for A of t. So that's convenient, and you can solve it easily. And you can expand this rational function into partial fractions if you want to get an exact expression for A of n, or the asymptotic behavior, which is 2.41 to the n. So we are, of course, exponentially small in the class of all self-avoiding walks, which grow like 2.64. Okay. Talking about generating functions, so you can see on these examples that they are most likely very useful tools. So in general, we have a set of walks, say, equipped with a size, and there's a finite number, A of n of objects of size n, and we put these numbers as the coefficients of the generating function. Here's a little notation that I will use. So the nth coefficient in this series is denoted like that, between brackets. So we've seen that they are convenient to solve certain recurrence relations. In fact, in many cases, you have a very simple dictionary that converts constructions on the objects into constructions on the corresponding generating functions, and that does not go through recurrence relations. So that's very pleasant. You work directly with the generating functions. So here are some simple entries in this dictionary. So if you are counting the union of 2 sets, you have the sum of the generating functions. This example will be used in what follows. So if the objects you want to count are defined as sequences of arbitrary length of objects of another class B, then the generating function is 1 over 1 minus B. This is very standard. Okay, so assume we have obtained a generating function. What are we going to do with it? Well, in the simplest cases, we can extract the nth coefficient and get a closed form expression. But in general, we should content ourselves with an asymptotic estimate of A of n. And this can be often derived from how the function, which is now seen as a function of a complex variable t, how the function behaves in the vicinity of its dominant singularities. These are the singularities of smallest modulus, so on the circle of convergence. So this should not be surprising. I mean, we have all learned that a series has radius 1 over mu if and only if, well, these are positive coefficients, the lim sup, or the exponential growth rate of the coefficient is mu. So this is the first elementary connection between the singularities of the function and the growth rate of the coefficients. Tony, you're not supposed to sleep during this talk. But you can go much further, and actually, so this was just dealing with the position or even the modulus of the dominant singularities and the exponential growth rate of the numbers, but you can go further and relate the position and nature of the singularity of the series to the more detailed asymptotic growth of the coefficients. So, for instance, under certain hypotheses, if you can prove that your series has a unique dominant singularity at 1 over mu, and has an algebraic singularity of this type, then you can transfer this singular behavior into an asymptotic behavior of the coefficients. Okay, so we'll see examples of that in what follows. So yeah, it was our case with this simple rational function. Okay, so what is very interesting when you want to deal with the random objects of a large size is to play or to handle multivariate generating functions. So for instance, assume that in addition to the size, which is the main parameter, say the length of the walks, you are interested in some other parameter p, which is defined on the objects, and you are able to compute this two-variable generating function, then you can extract from it by differentiation, say here the expected value of the parameter p taken on a random uniform object of size n. So that's just by extraction of coefficients. So if you can do the asymptotics for this series and for that series, then you get the expected value of your parameter p. But in fact, this series captures much more. It captures, of course, the whole distribution of the parameter p. But in this talk, I will just talk about expectations. Okay, so for instance, so let's go back to our rather dull walks, so our toy model, partially directed walks, no self step. So it's easy to compute the two-variable generating function that keeps track of the length of the walk. So that was our first variable t, and the number of north steps. Okay, that's again a rational function. You can play this game, take the derivative, and you get that the expected number of north steps grows linearly, as we could expect, which makes the end-to-end distance linear, and this class rather dull, in fact. Okay, so I now want to move to more serious models. So I've spared you this one. So we've so far discussed this one, and there has been a few generalizations, not that many, because it's not so easy to invent a model that can be solved exactly. Quite a few people have worked, and first independently, on a very nice class that has a natural definition, which are the so-called prudent walks. But I'm not going to talk about these ones. I'm going to talk about a slightly more recent class that we studied with Axel Bacher, and which happens to have a larger growth constant. And this one actually is easier to solve than that one, which is not completely solved, I would say. Okay, so I want to tell you what are these weakly directed walks. The terminology is not very nice. We had the partially directed walks, and now they are weakly directed. I would be happy to have a better name for them. So we will focus on actually weakly directed bridges, even though we have counted all walks of this type. So first, what is a bridge? Well, it's a self-avoiding walk like this one, meaning that the height or the ordinate of the starting point is minimal among the ordinates of all points of the walk, and the ordinate of the endpoint is strictly larger than the ordinate of all other points. So they are spread out, if you want. If we could count bridges, we would be very happy, because it's known that they have the same growth constant as general self-avoiding walks, but we are just going to count these weakly directed bridges, of course. The reason why they are so convenient is that you can concatenate them, and that's why they have been widely used. So we say that a bridge is irreducible if it's not the concatenation of two bridges. So for instance, this bridge is not irreducible, and it's the concatenation of 1, 2, 3, 4, 5, 6, 7 bridges, which you can find by taking the horizontal lines of the dual lattice and looking at those that intersect your path only once. And this tells you where to split the path. And that's where you see that a bridge is just a sequence of irreducible bridges. And this is correlated to this little dictionary I've shown, how you count sequences of objects. Okay, so let me come now to these weakly directed bridges. The definition that I give here is simple. It's actually not the original one. There was a more natural one, but it boils down to that. So we say that a bridge is weakly directed if each irreducible factor in this bridge avoids one of the, is partially directed, that is, avoids one of the 4 steps. And in fact, when you chew this for a second, you realize that it means that every irreducible bridge is one of these, is either north, east, south. So this one is north, east, south, the first factor, or north, west, south, like that. So they are partially directed either to the right or to the left. Okay, so we want to count these weakly directed bridges, and since they are sequences of irreducible partially directed bridges, we actually only need to count north, east, south, say, by symmetry, bridges. And here's the result is not hard to obtain, in fact, provided that you fix the height of those partially directed bridges. So this tells you that for a given k, the generating function of north, east, south bridges, these are possibly irreducible, of height k plus 1, is a very simple rational function with a numerator t to the k plus 1. Nothing is simpler. And the denominator is a polynomial in t given by some recurrence relation. So that's not a very compact form, but it's some form. No, this is all bridges. But then we'll get the irreducibles by saying that these ones that we can count are sequences of irreducibles. So one way of proving that is considering at the same time north partially directed excursions, which are the walks that start at level 0 and at 0 and are always non-negative. And I claim that there's a similar looking rational generating function for excursions of height at most k. And you can prove these 2 formulas together by induction on k by drawing some little pictures. So essentially you factor bridges or excursions at their last return or first return to the origin. And it gives you certain recurrence relations. Maybe we can detail the first one. So I'm considering a bridge of height k plus 1, and I say that, well, maybe it never returns to level 0, which means that it is a north step followed by a bridge of a smaller height. This gives me this term. Or it gets back to 0. I look at the final, at the last moment where it is at 0. After this moment, I have the same picture as here, and before I have an excursion followed by a horizontal step. This gives me this term. And so you have a pair of recurrence relations, which, when you solve them, gives these 2 results. Okay. So where do we stand? We have counted partially directed bridges, those that say go to the right. And that's basically the end of the story. So we sum over all possible heights. So that's not a very condensed expression for the generating function, but I'm not sure there is a simpler one. Since these partially directed bridges are sequences of irreducibles, then we know what is the generating function of irreducible partially directed bridges. And then we get back to the walks we want to count. They are sequences of irreducible bridges that are either like the ones we have counted or just the symmetric ones. And so you have again this sequence construction. So you could think it's 1 over 1 minus 2i, but there's the bridge reduced to a north step, which is counted twice. So it gives you this expression. Okay, so this is one expression for the generating function of weakly directed bridges in terms of a B, which is an explicit sum of rational functions. And so, of course, we can ask whether this is, well, we can ask several things. Is that, do we need to have such a complicated expression? Could we simplify it? And then, of course, we want to know how many weakly directed bridges there are asymptotically. So I want to say a few words first about the nature of this generating function. So for my toy model, we had a very simple rational series. And here, what we have proved is that this series is inherently much more complicated. So we have this B, which is, well, equivalent to our series, which is the sum of rational series. And so we can think that we will run into trouble, that is, we will have a singularity each time these polynomials gk cancel. It's likely to give us some kind of pole. And so we can plot the zeros of these denominators gk, so when k is 20. And what happens is that they accumulate on 3 parts of the complex plane. So you have 2 segments here and there, and then this curve. Okay. And in fact, we can prove that if you remove from the complex plane these 2 segments and this curve, which is an algebraic curve described explicitly, then W is meromorphic on this domain. Well, it's not a domain, on this part of the complex plane. And in fact, we were able to prove that this curve here is a natural boundary of W, of our generating function. That is, there's no way you can have an analytic continuation when you arrive close to this curve. So far, we have not proved that the segments are natural boundaries, but it's likely to be the case. So in particular, we have infinitely many singularities, and so this series is not rational, it's not algebraic, it's not what is called definite, so it's an authentically complex series, if you want. Okay, now regarding the asymptotic behavior of the number of weakly irreducible bridges, well, it's much simpler than this rather complex picture. So in fact, in a certain disk, you have a unique pole, which is simple. And so these transfer theorems that...
This comes from the denominator in this?
Yeah, exactly. That's where so the denominator was 1 minus 2 times the irreducibles, and that's just the denominator that vanishes. And we can locate this pole, which gives you a growth constant of 2.54. That's what it is. We can take, in addition, not the number of north steps, but say the number of irreducible bridges that you concatenate to form your weakly directed bridge. And so the number of irreducibles with this additional variable x. And from that, you derive that, again, the number of factors, which is a lower bound on the end-to-end distance, grows linearly. And so, again, we have a disappointing class of walks. And we've been able, that's not completely obvious, to generate these weakly directed bridges uniformly at random. And so here's one of size about 1,000. So here we have zoomed, and what happens, as you can somehow see, is that each of these irreducible factors is very small. So you're just stacking very small irreducible factors, and this explains why the length is linear, the end-to-end distance is linear. Okay, so I just want to mention a few other classes that are or may be also exactly solvable. So there's these prudent walks for which we have a functional equation for the generating function. So it's not too bad. In particular, one can generate the numbers in a polynomial number of operations, which of course is not the case for general self-avoiding walks. There's a conjecture for the growth constant, but at the moment we cannot solve this functional equation. We cannot prove that the growth constant is what it's conjectured to be. And another question would be to prove that these prudent walks, you have an example here, are in fact also disappointing. That is that they choose one of the two diagonals, if you take a random one, and they tend to stick to it. So I think that the limit, if this is your square lattice and you have one of these prudent walks, it seems to choose one of the quadrants and stick to the diagonal. So, but this, we don't know how to prove that. Then my former student, Axel Bacher, he has designed a rather strange class of walks, very unusual, that gives a rather unusual functional equation. I have never seen anything of the sort, and we don't know what to do with the functional equation. The growth constant seems to be a bit better than the one of the class that I've just shown you. Then with someone named Pascal Préat, who was actually one of the inventors of these prudent walks, he has a notion of k-fractal self-avoiding walks for which there is a hope to reach at last a sublinear end-to-end distance. But I really don't know at the moment how to prove this. And then we could try to make mixtures of these prudent walks and of the weakly directed ones by looking like that. I've not told you what is a prudent walk, so it's probably not very clear, but we could look at bridges whose irreducible components are themselves prudent walks. And this would obviously improve the growth constant. But okay, so I stop here. Thank you.